Good morning, everybody. So today, I will went over problem 1 on the 16 worksheet. The main concept we're gonna cover is flow to sphere. Okay, so let me write down. So main concept, flow through sphere. Okay, so flow through spheres. Most of the time, you notice that the notation is the only thing that is changed. The physical principle is very similar what compared to what we did with the flow through inclined plane. If you remember this type problems, right? This you have flow through a sphere through inclined plane. The derivation is very similar. It's just that they introduce some new name and new term that we need to get familiar with. Okay, so what are those name and terms? Okay, let me firstly introduce those. So the list of notation, this worksheet is being used. List of notation used in this worksheet. You have B, which stands for buoyancy, and C. Okay, you have G, which stands for gravity. You have S, which stands for sphere, and you have F, which stands for fluid that sphere are submerging. And lastly but not least, you have T, which stands for the terminal velocity. Okay, so terminal velocity and sphere is probably the new terms you encounter in this chapter. And usually the problems will give you some numerical values which is given, and they will ask you to find either any of these terms, whether it be the terminal velocity, the density of the fluid, or the viscosity. Okay, so what is given to us? So what's given? So it's given the diameter is 1 millimeters. So in this case, I will convert everything to SI units. Okay, it's always a good idea to keep things consistent. So I convert 1 millimeters to 10 to the negative 3 meters. The density of, okay, what's S? The density of the sphere is 7,870 kilograms per meter cube. The density of the fluid that the sphere submerged in is 1,052 kilogram per meter cube. Okay, the viscosity is 0.1 kilogram per meter times second. So what the problem want us to find? The problem want us to find the terminal velocity. Okay, so problem want us to find the terminal velocity in centimeter per second. Okay, so this is the general overview of the problems. Let's see what is the concept and formula we will use. Okay, so I just want to start with this problem by telling you guys the direction of the forces. So FD stand for drag force. Okay, and drag force has the opposite direction with the velocity of the ball. Okay, let me write. Drag force has opposite direction with the ball movement. So what does it mean? So in this case, since the ball is falling, the drag force will have upward direction. So drag force I'll write FD. FD will have upward direction. Okay, so and like I said before, this new concept, flow through spheres, share a lot of similarities with the fanning friction factors and the Reynolds number. They just changed a little bit. So what changed? So in the past, your fanning friction factor is calculated. Okay, let me change my different color. In the past, your fanning friction is calculated as F. F equal to the shear stress over 1/2 density times mean velocity square, right? Now, your fanning friction factor is calculated is instead of using FF to represent it, now they use CD. Okay, you find it in your textbook, and it is calculated as the force over area as the numerator, and the denominator to be 1/2 rho F times UT square. Okay, UT here is not UT Austin. UT here is the terminal velocity. Rho F is the density of the fluid. Okay, and if you simplify this further, if you put AP down, you get drag force over 1/2 AP rho F UT square. Okay, this is a new formula we will use for this new chapter. They just changed a bit. You see, it's very similar to the fanning friction we have. It just changed a little bit. They introduced the drag force. That's pretty much it. And what about a Reynolds number? Okay, so the Reynolds number, it used to be rho UM mean velocity times diameters over viscosity, right? Now it become, it's still Reynolds number, but now it's the density of the fluid, rho F times terminal velocity UT times diameters over mu. Okay, yeah, that is the new formula. As you can see, it's very similar to the fanning friction factor and the original Reynolds number. They just changed a little bit. One introduced the drag force, and one introduced the fluid density and the terminal velocity. Okay, so now we have all this formula in our hand. We can start to solve the problems. Oh, by the way, in the textbook, use the velocity, the volume is usually written in a weird way. Let me explain to y'all why it's happened. So in the textbook, let's derive it. So the volume of the sphere, so I call it V. Okay, the volume is V. So what's the volume of a sphere? Is 4/3 times pi times r cubed, right? Let's write this in term diameters. So it will be 4/3 times pi. R radius you replace by diameters over 2 cube. So it will be 4/3 times pi times d cube over 8, which would be, if you cancel this out, it would be 2, so it would be pi d cube over 6. Okay, this is the formula will be used for the volume. Now, in the next part of the video, I will derive the relationship between certain parameters, and I will try. Let's see how we can solve for the terminal velocity via iteration. Thank you for your attention.